Hello and welcome all. Today we are tackling another HackerRank problem called Beautiful Quadruples. This is a medium difficulty problem. Let's get into it. We call a quadruple of positive integers, w, x, y, and z, beautiful if the following condition is true, using w and then the bitwise XOR operator. So w XOR x XOR y XOR z is not equal to 0. Given a, b, c, and d, you count the number of beautiful quadruples of the form w, x, y, and z, where the following constraints hold, and essentially you get the value for w as a sort of variable when you go from 1 all the way up to a, and all values in between are what w will take on, as well as x, y, and z for b, c, and d respectively, and you basically make all the different combinations for those numbers. You should consider two quadruples as the same. If the following are true, they contain the same integers, and the number of times each integer occurs in the quadruple is the same. So for example, basically just 112 or 1121 is the same because if you rearrange the same numbers around, it's the same thing basically. So effectively, the order doesn't matter when you're counting these. We're also told some constraints that the values for a, b, and c, d could possibly go all the way up to 3000. So just to showcase why the order doesn't matter in this sense, because we're told that we're doing XOR on all these values, I'm going to go into Python real quick, and we're going to look at what happens if you do 1 XOR 1 XOR 1 XOR 2, and we see the value is 3. But if we do 1 XOR 1 XOR 2 XOR 1, guess what? It's the same thing. Order doesn't matter when you're doing bitwise operations. All right, folks, I'm going to give you some time to do it on your own, and I'll come back with my solution. Good luck. Since we'll be talking about the XOR operation, I think it might be relevant to review bit manipulation. Now, for those already familiar, you're free to skip ahead, of course, but if you could use a little refresher, we'll first need to review what bases are. Let's take the number 27, for example. As we're familiar with in base 10, the first position, which is the 7, 1 position. The next number over is 10 to the 1 power, or the tens position. Now what we can see here is that when we take 10 to the 0, and that's the ones position, we can take whatever number is represented there and then times it by that value, the 1 in this case. So the 7 times 1 is 7, of course. And for the tens position, you would take 10 to the 1 power, or 10, and you multiply by 2. And so you can take those two numbers, 20 and 7, and add them together, and you get 27. Now, it is kind of silly to take a base 10 number and represent it as the same base 10 number. This is just so you can get a base understanding. Get it? Base understanding. So with base 2, the same thing applies. Each position is just the base, or 2, to the 0, and then to the 1, to the 2 power. What's interesting about the base 2 is there are only two numbers, or two symbols, that are used. That's 0 and 1. The literal 2 is not going to exist as a symbol in that base. Base 10 does not have a single symbol for 10. Typically what you would do is you would take sort of the largest possible value. In this case, 16, 2 to the 4th power, is the largest value without going over. That'd be actually 32, which is more than our 27. So we wouldn't go that far. We just go to 2 to the 4th, or 16. So you can kind of see what our total looks like. We'll currently have 16. We go to the next position, the 2 to the 3rd, or 8. And we would say, okay, there's sort of room for 8, so we put a 1 there. And then to the 2, we have a 4. If we added 4 to the total, that would actually go over. So we know that that's a 0. We can't fit that. And then the next position is the 2 to the 1. And we know that we can add 2, so we have a 1 here. And then to the 0 or 1, we would say, okay, that's exactly going to add up to 27. And so if we want to represent the value of 27 in base 2, we would represent it as 11011. One thing you'll notice is that the smaller the base, the less room you have to fit value in the individual digits. So here are some numbers just as an example. We have 27 like we just did. Here's what 3 looks like, and here's what a 5 looks like, and here's an 8. Pause for a second and kind of reason for yourself why these make sense. Okay, so now that we talked about bases, let's move over to bit manipulation. So the first thing to keep in mind is that when we're talking about bit manipulation, we're just talking about taking two numbers in base 2 and doing some simple operation to them. Each position is called a bit. That's hence the name, bit manipulation. Let's say, for example, that we want to use the AND operation, and we have these two numbers, 3 and 5. So the AND operation will say, for each position, if both values are true or 1, then the result is 1. Otherwise, the result is false. If we do the AND operation between 3 and 5, we get this result where only the 1 position is actually on or true. The result here is 1. This is not math that we're doing addition, even though the word and might imply that. That's not what this means. The OR operation, it kind of has a similar simplicity to it. You're looking for each position or each bit. If either value is true or 1, then the result is true. That means if both are 1, that still counts. So anytime there's a 1, then the result is true. We're going to do 3 or 5. And we see that in the 1's position, there are 2 1s, so that's definitely going to be true. We see another 1 here in this column. And the second we see these 2 zeros, we know, oh, that's false. When we do 3 or 5, we get 7 as the result. All right, I think this sets us up perfectly now for XOR, because the XOR operator says that for each position, if 1 and only 1 of the values is true, or 1, then the result is true. Otherwise, it's false. You're looking for exactly 1 1 or 1 true. So we see here the first position, there are 2 1s, so we actually have a 0 there as a result. For the second, we have a 1, again, a 1 after that, and then 2 zeros, that's also false. So when we do 3 XOR 5, the result here of 6. Now, one thing you will start to realize here is that you can start sort of drawing some observations here. For this example, we'll use the value 13 and 7 and do XOR on that, and we get a result of 10. What's interesting is if you flip the 2 and we have 7 XOR 13, we'll get the same result. When you're doing operations with bit manipulation, the order does not matter. Let's take the number 11 and do XOR with itself. We'll see here that the result will be 0. This should make some intuitive sense given how XOR works. Any number on top of itself will have exactly perfect alignment to be false for everything, or 0 for everything. So one other observation we can take here is, on the flip side of that, if we do a number, any number XORed with 0 will result in that same number. Again, intuitive sense here, because all the bits that are on or are true, or 1, these are all the same thing. Any number that's on for the first number will remain on when you do XOR with 0 because of how XOR works. All right, we can now begin to break down our problem. So we're going to be given 4 numbers, A, B, C, and D. And we're going to need to return this count of unique combinations. And what's funny is we're going to be dealing with another set of similar variables called W, X, Y, and Z. Hopefully it's not too confusing. I'm trying my best to keep the colors matching, and I'm trying to keep the context where it should be. Each value for A, B, C, and D is going to have a combination with each other such that 1 through A and all the values in between are going to be considered. And that variable is going to be W. And same thing for X, Y, and Z for B, C, and D, respectively. Okay, hopefully that's not too confusing. I'll try and keep it consistent moving forward. We're told that a beautiful quadruple is a combination such that the W XOR X, XOR Y, XOR Z is not equal to 0. So first, let's rewrite this big equation we're told of the XORs. And one thing we can keep in mind is that order doesn't matter, as we've seen before. And we can essentially break these down into 2 separate groups. The W and X as its own group, and the Y and Z as its own group. We can actually do the XOR operation on those 2 groups individually, and then we can XOR those results together to get our actual answer. Let's separate them into 2 groups. Given our understanding of XOR, we should understand that the first group cannot be the same number as the second group. If they are the same, we would get 0, and that's a problem. The first group, W XOR X, cannot equal Y XOR Z. That's another way of thinking about it, so hopefully that'll make things a little bit easier to understand moving forward. So let's go over a quick brute force method, which should be fairly intuitive. What we can do quickly is just go over all possible combinations, check the results, and then just add to a running total, and then return that total. And that's basically it. Here I'm going to define a Python function. It doesn't need to be Python, obviously. I'm just giving it as an example. But we have our A, B, C, D as givens. We have a running count, and then we're going to have just a bunch of nested for loops for A, B, C, and D, and their corresponding value, which will be the actual values for each combination as W, X, Y, and Z. At the inner for loop, we're going to actually do our check to see if W XOR X, XOR Y, XOR Z is not equal to 0. And if that is the case, then we can just increment our count, and then at the end, return our count. One pretty big problem, though, is that we're told in the problem that the values for A, B, C, and D could potentially be as high as 3,000. So given this nested for loop that we're doing, that would be 3,000 to the 4th power, which is some crazy amount of combinations. It's going to take forever. This is not a very efficient solution. So what can we do to reduce complexity? One thing I like to do on these kinds of problems is to recognize a kind of pattern if we possibly can. So let's try and do some pattern recognition, see what we can observe. One thing that we're told is that when we're counting the numbers and we're seeing the combinations, we have to essentially make sure we're not counting any duplicates. For example, a 1112 and a 1121, that still has 3 ones and a single 2, right? So it still counts as the same thing, and it should only be counted once. We should also remember that from our understanding of XOR, order doesn't matter. And as we just discussed with the duplicates, the order doesn't matter when you're counting it either. What we can do is recognize that the A, B, C, D order also doesn't matter. We can actually sort those in order to ensure that the A, B values are always the smallest 2 values, and the C, D values are always the largest 2 values. And this should make some intuitive sense, because when we're given an example of 7258, it's going to give you the same result, the same total number of unique combinations as 2578. One thing we can do is actually store or memoize the combinations for all values that are for Y and Z combined together. And we can actually use that for the W and X. Now, the reason we can do that is because if we're doing the sorting, we can ensure that the C and D value are the highest, the largest 2 numbers, and therefore all combinations between Y and Z, which are the associated values, are going to capture all of the other combinations are going to be found within the WX combinations. So let's go over a quick example. So let's take an example here as 4212. We know we can sort this really quickly to 1224, and we'll enforce our rule that the combination between the first group W and X is not equal to Y XOR Z. Let's check out all the combinations for W XOR X first. We see that we have 1, 1 and 1, 2. That's it, because A and B is just 1 and 2, and we count all values from 1 up to each one of those numbers, and that's the combinations that we can see for the left side. What about the right side? We see that we get 1, 1, 1, 2, 1, 3, 1, 4, as well as 2, 1, 2, 2, 2, 3, 2, 4. And those are all the combinations on the right-hand side. Now you'll notice that we have a bit of overlap, and this is what I was talking about before. Because the left side has the smallest numbers and the right side has the largest numbers, all of the combinations on the left side will be contained as a subset within the larger numbers on the right side. So we don't need to calculate things twice, essentially. We just need to do it once with the 2 largest numbers, and we'll have those calculations ready, and we need to consider them for later. Essentially, we're going to be pre-computing these combinations. Okay, just as an aside, I want to kind of see what the end result would be if we were to do all the combinations here. We want to combine them so that we see all the WXYZ combinations that are possible. So here they are. It seems like not that many. There are 16 total. So as a reminder, we are doing the XOR operation such that if we combine all these using the XOR operation, we cannot get 0. First, let's look at duplicates. Here are the same numbers. I'm just highlighting the ones that are duplicates in a gray little box. This is adhering to that restriction that all the combinations need to be unique. The order doesn't matter, so all these are effectively duplicates. We would want to reduce them by eliminating them and having only one unique one, and then we'll eliminate all invalid combinations. Again, using XOR altogether, these cannot equal 0, so the values 1, 1, 1, 1 would reduce to 0 using XOR, and the same thing with 1, 1, 2, 2, because those would actually cancel each other out and become 0 as well. And then we're left with these values that all are unique and are valid. And so these would be the 8 unique combinations that would answer the question of what would you get for a 1, 2, 2, 4, or any other combination of that as a result. All right, let's check out an algorithm. And the first thing I'll note here is, just like we saw, we're going to first count all combinations, and we'll try and remove duplicates, and then remove invalid combos. But let's go through them. So as a similar example, we'll have the 4, 2, 1, 2. Right off the bat, we're going to sort them into 1, 2, 2, 4. Then we'll focus on just the 2 largest numbers. One question that you might want to keep in mind is, do we actually need to make all combinations between Y and Z? Here are all the combinations. Let's go back for a bit. So here I've highlighted all the duplicates again. So let's just focus on the C and D values, since that's the ones we're dealing with right now. We should recognize that the flipping of the 1 and the 2 doesn't change the end result, right? So these effectively are duplicates we can eliminate sort of at the start. When we're making our combinations, we can just ignore any combinations where the Y value is greater than the Z value. This is for a few reasons, but effectively, I'm aiming to keep everything as sorted as possible. I want the 1 to come before the 2. We still have all of the combinations that are valid. Now, how do we handle the other duplicates? We'll talk about that later. Okay, so to answer the question, do we need to make all combinations? The answer is no. We can ignore combos where the y is greater than the z. And in that case, we can eliminate this one here. And let's check out what this would look like in a programmatic way. So first, we can go through a basic for loop where we're going through C first, 1 through C, and that'll be the y values. And in order to ignore the times when z is actually less than y, when we're going through the values for z, we can actually just start out on the y value. So this is a simple way of enforcing this rule. But then we have a result here of the combination of y, x, or z. What do we do with it? Here are the combinations again. And what we'll be doing is storing them in a list, essentially. We're going to memorize them. And we're going to look at the result. So in this case, 1x or 1 is 0, 1x or 2 is 3, and so on. We're going to be using those values as the index within our list. So here's our memo list. We have a running count of 0 so far. We're going to go through each one and actually add them to our list. So for the first one, 1x or 1 is 0. So at the 0 index, we're going to add that value. For 1x or 2, that's adding to the 3 index. For the 1x or 3, we're adding to the 2 index, and so forth. So in the end, we have a count of 7. Okay, so now that we've essentially pre-computed our combinations, and these are, keep in mind, these are all the possible combinations with all combinations stored, let's actually handle the full set of W, X, Y, and Z combinations. Sort of put them all together to kind of see how they work. Well, let's first start off on the left-hand side and grab the A and B. We're going to just append them to each iteration of the value for W and X. So let's intuitively consider the first WX combo, which is 1, X, or 1. We're just going to combine all the YZ combos, which is what we already have in our list, to those. And this is what it looks like. I'm just going to clean up the list a little bit, and we're going to combine them. And here's what all that looks like together. Now, the question here is, how many final combos are there? And you might intuitively say, well, it's 7, because we had 7 total, and each one is being sort of appended to the 1x or 1, and you'd certainly be right. We just look at our combo count, and that's how many there are. But are all these combos valid? And remember our rule, where the value for the first group cannot equal the second group. And in fact, we see that we do actually have some situations where they are equal. That's a bit of a problem. How do we account for those? How do we eliminate those? Well, we can separate them because in our memo list, we actually sort of have that information of which values equals the 1x or 1. And that would be at index 0. How did I get 0? Well, again, it's just the index of 1x or 1. So we can check all those values, and we see there are actually 2 of them there, and those are the 2 counts that we want to eliminate. We don't want to consider these since they're invalid. We can actually take that count from our memo list and subtract it from our total, and we would get 7 minus 2. So let's put that to the side, and let's intuitively consider the next W and X combo, and that would be 1x or 2. Again, we're going to take all the values from the memo list, append them, and here we can check to see how many we have. We have 7 minus 1, given the 1x or 2, so that's index 3. We see there's only 1 count in there, so we subtract that from 7, we get 6. So we have 6 total combinations. And now we have a final answer of 11. But you might be wondering, well, hold on, we did this already. We looked at all the values. There should only be 8 unique valid combinations. We must have done something wrong. Let's go back for a second. What did we do wrong? For those with a keen eye, you'll notice that we actually have duplicates. These are the ones where the order was rearranged, but they should be counted only once. So this is a bit of a problem. We need to kind of figure out how to handle these sort of extra duplicates. And let's first notice any patterns that we might find here. What can we notice about these? You'll see that on the right-hand side, the kind of sort of new combinations, all of them have 1 at the Y position. Why might that be? Let's go back a second to when we first were considering these duplicates. Let's take note of the order within each duplicate. Ideally, we would want to keep just one of these values, and I'm going to select the one where all the values are sorted. It's nice and easy to kind of keep track of, especially when you're looping through numbers. It's nice to just keep things in a sorted order. So if I had a preference, I'm going to pick the first one here because those are all sorted in increasing order from left to right, and I would preferably want to ignore the rest. Well, how do we ignore those? We need to be able to recognize them somehow. So what is the quality? What makes us understand that these things are not sorted? I want you to take note of the Y and X values for each one of these duplicates that we're going to kind of eliminate. That's sort of the dead giveaway. That lets us know this thing isn't sorted. When the X value is greater than the Y value, sort of by definition, it's not sorted, right? So that will be our way of signaling in our code, hey, this value shouldn't be considered anymore. You should remove it. You should eliminate it. So what we're going to do is when we're done processing one value for X, for example, X equals 1, we would eliminate all the combinations where y equals 1. The reason for that, and this is essentially going to be a cleanup step after we're done processing the values for x equals 1. The reason for that is because once x goes to 2 and we process that, there is no situation where we're going to want to keep the values for y that are less than 2 at that point, right? So we can just eliminate them from consideration, because in the future, there's never a time when we're going to want to need them. We're going to want to eliminate them because they're at that point captured the first time, and we want to remove the future duplicates, and that's why we want to do that as a kind of cleanup step. It might be a little confusing now, but let's actually go back and go over it to see what it looks like. So here we're going back to when we first finished processing the first combo of w and x, the 1 XOR 1. So this is where we would then do our little cleanup step. We're done processing all combos for x equals 1. We'll want to remove them for future redundant XOR z combinations. I'm talking about all the values where the y is equal to 1, essentially. So those are the combinations we want to remove. We want to clean them up before we get to x equals 2. That's 1 XOR 1, XOR 2, XOR 3, XOR 4. We're going to clear them out of our memo list, as well as update our count. So our count is now 3, and once we removed all of our combinations that are sort of redundant and will only lead to duplicates, we can now intuitively consider the next w and x combo, which would be 1 XOR 2. And we're going to do what we did last time. Take all the values from our memo list, combine them with our 1 XOR 2, and we have these 3 combinations here. We check to make sure that there are no values that are essentially invalid, and of which there are none. We have 1 XOR 2, which is 3, so that index has nothing in it, so we have 3 minus 0 to equal 3. Next, we're going to remove all the future duplicates that we don't want to consider ever again, which would be where x is 2 and all the values for d or z value. So 2, 2, 2 XOR 3, 2 XOR 4. So we'll remove those. Doesn't really matter too much since this is the last step, but we're going to clear out our memo list and essentially have a count of 0 at this point. But we are effectively done because we've taken all considerations for the combos between A, B, C, and D. And we have a total here of 8, which is exactly what we were expecting. Now, I know that was a lot of stuff. I'm going to go over a little bit of a more involved example. I didn't really get to showcase this idea of the cleanup step. All right, let's say that we're given 3, 4, 2, and 3 as our A, B, C, and D value. As we've been doing, we can sort that into 2, 3, 3, and 4. Next, we'll take our 2 largest values, the C and the D, and we're going to look at all the combinations for that. And we have those here, and we're going to plug them into our memo list and keep a running count, of course. I'll keep it simple and do that fairly quickly. Here's where we start processing each value for x. We're going to first process by x equals 1. All of those combinations we process at once. There's only one combination where x is 1, and that's 1 XOR 1. Again, we take our combinations from our memo list, plug them in, take our count minus whatever the value is in our memo list for that particular XOR, 1 XOR 1, and we have 6 for this. Then we do our cleanup step where x is 1. So we do 1 XOR 1, all the values for d essentially. Once we clear them out, we'll have a total count of 5, and then we go to the next x value where x is 2. And again, we process all the combos where x is 2. Since our A is 2, we have to process 1 and 2 for that. So it's 1 XOR 2 and 2 XOR 2. So let's process those together. For the 1 XOR 2 combo, we have 5 minus 0, so that's 5. And for the 2 XOR 2 combo, that's actually 5 minus 2, so we have 3 for that one. Let's put them to the side, and here's where we do our cleanup step. We're cleaning up all the x equals 2 combos. So it's 2 XOR 2, XOR 3, and XOR 4, and take them out of our MMO list. And we have a count of 2 now, and we process now x equals 3. There are only 2 possibilities for that, because again, A is 2, so 1 XOR 3 and 2 XOR 3, and we'll process those together. I'll shrink our value so far, because that's taking up a lot of space. And there are only 2 combos to really consider. We have 2 minus 0 for the first one, and 2 minus 0 again for the second one, so all these are valid. We add them into our total. And again, we do the cleanup step at the end. So we're cleaning up all the x equals 3 values, 3 XOR 3, 3 XOR 4. That's essentially clearing out our memo list, and our count is now 0, and we are done, because those are all the combos between A and B. We have a total of 18. All right, so let's check this out in some code. All right, I'm going to be doing this in Python, but I will provide a JavaScript solution in the description. So first off, we're going to start off with our function definition. I'm going to sort A, B, and C, D, and then I'm going to sort of reassign them into similar variables, capital A, B, C, and D, to work with in the future. Essentially, these are all sorted in increasing order from A to D, where C and D are the 2 largest numbers. And the next thing we're going to do is we're going to look at creating the memo list, but we need to sort of figure out what size to make it. Because of how the XOR operation works, you're never really going to go past the most significant bit. So as long as you get basically the largest number and you say, okay, the most significant bit is the max, that's as far as you can go, we can use that to essentially figure out exactly how large our list is. And we'll be using the bin function in Python. If you're not familiar with that, I'm going to showcase this real quick. So here I'm going to go into Python, and if we, for example, have a D of 16, that'll be the largest number, I would do bin 16. The OB signifies that this is a base 2, even though it's a string. 1 and then 4 zeros is how you would represent 16. That lets us know how many combinations we could possibly have, where each position here is going to be either a 1 or a 0. And that gives you essentially all the different possible combinations you could possibly have within that space. What we need is to take this size, which is essentially 5, and say, okay, that's the size. I need to take 2 to that power, to, in this case, 5. And how would you do that? Well, you would take, obviously, bin of 16. You would take the length of that, which is 7. But because we have these 2 annoying pieces there, we want to take that away. So we say -2 there. And that gives us the 5 we're looking for. And then we say, okay, we're going to take 2 to that power of 5. All this is saying is that if you take a 1 or a 0 for each of these positions and you look at all the different possible combinations that are within that space possible, then you'd have 32 different combinations. So that's exactly how big our list needs to be, because you can't go beyond that. Okay, so with that in mind, we are going to take that number, whatever the max is, and multiply it into our list. So we have a list of zeros that is exactly that length. So that is our memo list. And we'll also separately keep track of the total number of combinations that are within that list. We'll need to keep this in sync with our memo, but that's not too hard. Next, we are going to store all of the CD combinations by looking at the range between 1 and C, and then also Y and D, and that's our sort of nested loop that we talked about. So once we get our combination of Y XOR Z, we'll take that combination in our memo list and then add 1 to it, and as well to our total combos, because we need to keep that in sync. We'll go through all of these to get all the possible C and D combinations. Next, we're going to go through our total combinations. This is essentially our answer that we're going to be returning. And we're going to go through the full combination of W, X, Y, and Z all kind of put together. So one strange thing that you'll see here is the way this for loop is being ordered. It would be nice if we can do something similar like we did up here, where you're looping through the C and then the D, because you can keep the order in a kind of intuitive way where you have this, the Y being used as the minimum value for the Z within the loop. But because of how we're processing this, we need to process all of the X's first. So X of 1, we need to process all of those. Then when X is 2, we process all of those in the combination with W. So this does require a little bit of finagling here, but essentially what we're doing is we're looping through X first, we're looping through W inside of it. So we still want to have this inner loop cut off when X is essentially going past where A would be. So we want to set the max that we're going to handle within this is the minimum between X and A. Hopefully that's not too confusing, but essentially this is doing the same thing we were doing up here, just in a kind of reverse order where the inner loop is the W and the outer loop is the X. That's all. Anyway, we'll get to our WX combo. We're going to grab the information from our memo. Remember, this is where we're essentially going to be subtracting the combinations that kind of zero out the equation. So this is where we're grabbing that information. And we take the total, which is the total combinations that are within our memo list, subtracting those zeros out. And that's the additional valid combos that we're going to be adding to our total, which is what we're doing here. And then we do that for all of the W values. Remember, we're in our X loop. So once we're done with one of the X's, this is our cleanup phase. I put a lot of text here just to help out whoever is looking at this. Once we're, again, we're still within the X loop, then we are going to clean up by going from X up to D, and that'll be the Z essentially. And then we'll make our deduplication combo, which is going to be X XOR Z, and we're going to subtract it out of our memo list. And in order to keep things in sync, we of course subtract 1 from the total combos from the CD memo, and then we'll go on to the next X. Once you're done with this whole loop, we are essentially done with the entire process, and we can return our valid combos. Let's run some code. All right, great. Let's submit some code. All right, looks good. All right, let's check out some time complexity here. So first off, technically the sorting is constant because it's only 4 values we're always sorting, so there's nothing too crazy there. This is all pretty much constant time creating an empty list. This is not too bad. And here is where we start looking at some complexity here. So because we have a nested loop here, we're essentially doing big O of C times D, and that's all by itself. So that's nice. And then here we have a kind of nested loop here where within our B loop, we're essentially going through A, but then separately we're also going through D. So we have a bit of a wonky complexity here where we're doing B times A plus D. But these are separate, so we have this plus this, and that's what we have here at the bottom, and that is basically our time complexity. Big O of C times D plus big O of B times A plus D. Very wonky, but that's what you get when you have 4 different variables you're kind of juggling around. All right, folks, that is it for today. If this is the kind of content you enjoy, please make sure to like, subscribe, do all the good things, and I will see you next time. Take care.